Hello students, today we reached to the last topic of this exercise 1, that is measurement of time and simple pendulum. So we commonly use pendulum clocks in office or homes to note the time, which is based on the periodic oscillations of a pendulum. So a simple pendulum is a heavy point mass suspended from a rigid support. As you can see, this is the diagram, by a massless or inextensible string. So this is this is the rigid support, this is a bob, and this is the string with which it is fixed. Now moving to this diagram, you can see each and every point is labeled and explained. This is the rigid support written here at the top. Now the point of suspension from which the pendulum is suspended. A, B and C are the three positions of this bob. So B is the mean position. When it is in the center, it is the mean position. When it oscillates, the maximum place where it can go, that is the A, extreme position. On the other side, it is C, labeled as extreme position. Now this red is the bob, and the distance between B and C, the distance from B to C, is the amplitude. So these are some related terms regarding simple pendulum. Very first, oscillation. One complete to and fro motion of the bob. One complete to and fro motion. So suppose it starts motion from B, so it will go to A, and again it will go to C, and when it reaches to B, then we can tell it has completed one oscillation. Or suppose we are starting from the extreme position, that is from A, so when it will go to the another extreme position, again come back to the same position, starting point, that is A, then we can say that this is one complete oscillation. Now moving into the next topic, time period. This is the time taken to complete one oscillation. How much time it takes to complete one oscillation is the time period of a simple pendulum. It is denoted by T and its unit is second. Moving on to the next, frequency. It is the number of oscillations made in 1 second, and it is denoted by F or N. Its unit is S inverse. Amplitude. The maximum displacement of the bob from its mean position to either side is called the amplitude of the oscillation. It is denoted as A, and its unit is meter. In this diagram, you can see the place from B to A or B to C. We can label it as amplitude E. Since it is a distance, so its unit is meter. Effective length of the pendulum. It is the distance of the point of oscillation O to the point of C, from here O to B, and in this you can see here labeled also L. This is the effective length of the simple pendulum. Now moving to the next, that is the relation between time period and frequency. Already discussed also in 8. Frequency is 1 by time period, or time period is 1 by frequency. By substituting the value of T, we can calculate the frequency, how much frequency it can take, or if we know the frequency, we can calculate the time period of a simple pendulum. Moving on to the next expression for the time period of a simple pendulum. Before going to this, I would also like to discuss about the compound pendulum. Compound pendulum, that is any swinging rigid body free to rotate about a fixed horizontal axis, is called compound pendulum or physical pendulum. The appropriate equivalent length of calculating the period of any such pendulum is the distance from the pivot to the center of the oscillation. It is the distance from pivot to the center of the oscillation. So in your mind, one question may come: what will be the difference between a simple pendulum and a compound pendulum? So the main difference between a simple pendulum and compound pendulum is that in In a simple pendulum, the distance between the center of gravity of the suspended body and the axis of suspension is large compared to the dimension of the suspension body, whereas in a compound pendulum, the dimension of the suspended body are not so large, so we have to depend upon the pivot of the center of the oscillations. So a very good example of compound pendulum is the pendulum that is used in the clock, which is not a simple pendulum, is a compound pendulum. That is the body capable of oscillating about a horizontal axis passing through it. Now moving on to the next topic, to measure the time period. So we measure the time period of a simple pendulum with the help of these oscillations. While counting the oscillation, there is a chart in your book. The time period for pendulum of different length. Go through that chart. And this experiment we will do in this school in physics lab also to calculate the time period. We have an expression which is related to time period, that is T is equal to 2 pi under root L by G. This relation gives us that to calculate the time period of a simple pendulum. So when we square it, it will become T square. To remove this root, we will square it. It will become T square 4 pi square L by G. This is a square 4 pi square, where T is the time period, L is the effective length of the pendulum, and G is acceleration due to gravity. Now from this relation, two very important questions they ask, that what are the factors on which the time period of a simple pendulum depend. So very first, it is directly proportional to the length. Time period is directly proportional to square root of its effective length. So it depends upon the length. Time period is inversely proportional to the square root of acceleration due to gravity. So it depends on that also. G varies rarely, so only a limited condition. So it depends inversely proportional to square root of G. So these are the two factors on which it depends. One more question is that what are the factors on which the time period does not depend? So it does not depend, number one, the time period of oscillation does not depend upon the mass or the material of the body suspended. If we take two pendulums of equal length, but with the bobs of different masses or different material, their time period will remain same. Moving on to the next one, the time period of oscillation does not depend on the extension of the swing on the either side, that is on amplitude. It does not depend upon the amplitude. So this is a graph which indicates the relation between L and T square and how it varies. Here we have L on x-axis and on y-axis we have T square. X-axis unit is 10 centimeter and y-axis is 0.5 second per second square. So while counting the oscillations, if we know the distance and time, we can plot this graph. We will explain more in the next chapter, chapter 2, how to plot a graph. So to calculate this slope, we have a formula. Slope is equal to AB by CD, where AB is the distance from the higher maximum value minus minimum value, that is T1 square minus T2 square by L1 minus L2. Seconds pendulum. A pendulum with a time period of oscillations equal to 2 seconds is known as seconds pendulum. Here two numericals also we have discussed. The time period of a simple pendulum is given 2 seconds. What will be its frequency? So as we know, T is given 2 seconds. So substitute the value of T in the relation between frequency and time. We will get the frequency. Moving on to the next question, number 5 from your exercise 1C. Compare the time periods of two pendulums whose length is given 1 meter and 9 meter. This is one more question, that is compare the time period of two pendulums of length is given 1 meter and 9 meter. Question number 5 from the exercise 1C. So here given what is given, L1 is given 1 meter and L2 is given 9 meter, and we have to compare their time periods. We know the relation T is equal to 2 pi under root L by G, or so G will cancel, 2 pi will cancel, and we will get a relation that T1 by T2 is equal to under root L1 by L2. Substitute the value of L1 and L2. L1 is 1, L2 is 9. So T1 by T2 is under root 1 by 9. We know that the square root of 9 is 3. So we will get the ratio between these two time periods as 1:3. Very simple numericals are there from this exercise. I know you can do it. So try and please practice the solve example numericals from this exercise also. Few questions I have given as assignment. Try to do. Thank you.